Next talk will be Nestor Arsenov from Astronomy Institute of Sofia and Hungarian Observatory, and he will also talk about voids, but on bigger scale, not on local scale like Rosa spoke, but bigger scale with quasars.
Hello. Yes, my name is Nestor, and I'll be talking in the next few minutes about my most recent project concerning the use of quasars in what we call high redshift regime and looking for large-scale structure. So I'll just waste a little bit of your time to say that I'm a final year student at the Institute of Astronomy in Sofia. I'm supervised there by Dr. Lyuboslav-Chilamichova, who is dealing with properties of quasars, observing quasars, polarization effects, and I'm affiliated to the institute in Budapest too, because my co-supervisor is Andras Kovacs, the organizer of the conference, and he is dealing with large-scale structures and cross-correlation of primarily voids with CMB lensing effects. So we have this common project, which is my PhD thesis, and we also have a growing number of students here in Budapest and also on postdoc coming this autumn. We are dealing in this project with something like an expansion to what has been done with looking for voids at larger redshifts, and we're moving on to a regime of 0.8 to 2.2 with the data that we have available. Quasars are an obvious choice for us because of their luminosity, but for our work, they kind of present also a challenge due to their sparsity in comparison to other types of galaxies. So we had initially the open question if they will be dense enough for us to trace the cosmic structure. Spoiler alert, it's good enough, obviously, since I'm having this talk. Our work also displays that there is a need for using quasars at these regimes. The data that we're working on is kindly provided by colleagues from the University of New York. Kate Story-Fisher published the Quaia catalog last year that we are using. It's based on the Gaia sources found to be by using proper motions and color cuts to be quasars. So Gaia, color cuts, you get candidates to be quasars, and then it's also cross-matched with unwise, which gives you additional infrared channels. And the catalog contains around 1.3 million quasars, brighter than G20.5, covering almost the full sky. Where did I press? Pointer. Come on. Where's the pointer? Sorry, yeah. Almost full sky, except for the galaxy. This little GIF also shows you how this is supreme to SDSS in sky coverage, even though SDSS would be somehow deeper. Working with this, we proceeded in extracting just the redshift range that we considered of interest for us, where there was also some previous work done by Andras in SDSS. And we also decided to cut it at 0.8 and 2.2 to avoid these features here that might have then be later problematic. Additionally, we were provided with 50 MOOCs of Gaia by our colleagues in Geneva and Tenerife. Their work was led by Francisco Sinigaglia, and we are waiting for his work to be published soon, and we will deliver our results together with him. And Having all of this, we needed to find the voids and clusters with some kind of structure finder. Our usual choice is the revolver code that developed by Sash Nadador some years ago, which is based on the Zabov algorithm itself. And it's a code that I would say goes more or less in 3 stages, where the first one is to split the data that you have available, the data points in something called Voronoi cells. So it's tessellating the space around each quasar into the points in space that are closer to this particular quasar than to any other. And from this, you get a volume to each of the quasars or sources, whatever kind you're using. This volume you can convert into a density. In the next step, the Zabov algorithm merges the individual tessels into larger structures that eventually become the clusters and voids that you're interested in, based on a watershed approach that's also free of free parameters. This is another reason we're using Revolver. Conveniently enough, Revolver also contains the options that we all have used for applying the sky mass, because we were obstructed obviously by the galaxy, completeness correction due to systematics and dust contamination, and the redshift selection, as was mentioned before, the drop in density. Oh no, sorry, the drop in density due to sensitivity of the quasars. Thank you, Mina. Oopsies. A little bit nervous, yes. So first result, we get a catalog to each of our quasars that gives you, beside their coordinates, also the mentioned volume that we turn into density, and then you also have the raw volume if you for some reason don't trust the corrections that Revolver has performed. You have the source IDs in Gaia and Unwise in case you want to cross-match with other properties, you want to do some SQL search and extract them. And you also have in the catalog contained the properties of the void or cluster to which this quasar potentially belongs. Another data product, or rather two, are the catalogs of clusters and voids coming from Revolver. So for the redshift range that we were using, this would mean we provide 13,000 voids and 41,000 clusters, and they all come with the size of the structure, the most extreme density fluctuation of a Voronoi cell in the structure, the average density fluctuation in the whole cluster or void, and then something called lambda introduced by Sesh, which is the potence of the structure to voice the CMB. It's just the mathematical product of the size to the power of 1/2 multiplied by the density fluctuation. And it's a powerful tool actually in our field. And these are the data products that we're providing. With the next 2 slides, I just want to convince you that the statistics that we observe in our catalogs are also consistent with the mocks that we looked at. So what you will see here on the top is the distribution of the radii of the clusters in blue, the voids in blue, the clusters in red as histograms, and then the data point that you see on top in black are actually the average of the 50 mocks that we were working on. And I hope you see visually that they have a very good overlap, very well within the error margins. And we even do a visual inspection of the ratio between number of edge close voids and clusters to number of safe and edge distant voids and clusters. This is just kind of a test or a useful proxy for a future user if you don't trust structures over this limit to cut your data and stick only to sizes or other properties that cover this range. The same we did also for the density fluctuation of the most extreme cells in each of the clusters. Then also for the average density fluctuation of voids and clusters and their lambda potence proxy. And we conclude that the agreement is great, which also makes the mocks reliable, although the mocks were not tuned to satisfy these properties at all. We see that the edge effects in the data and mocks are consistent, and the users can perform on their own cuts at their own will. One last plot that I'll show is the one concerning regarding the density profiles of voids on the left and clusters on the right. We have performed 3 splits regarding the environment of the structures. So over here in dark blue, you see the profiles of voids located in larger underdensities, while in the light blue you see voids that are rather located inside some overdensity, and then in the center you have a void. Sorry, maybe at the back you don't see the axis. What you have on the y-axis is the density, and on the x it's the distance from the center. And then we stacked all of the detected 13,000 voids and 41,000 clusters to observe these profiles. And I hope once again you can see that the solid lines coming from data match very well the solid dots, which are from the mocks. And likewise, we also introduced in Dash these edge-closed structures from the data, and the empty dots are the edge-closed structures from the mocks, which also are consistent with each other. And they're even in agreement with previous works done by Station Adator, about which we are very happy. So in conclusions, we consider that in the observed redshift range, we have some reliable results, or we have proven that indeed we can use the quasars from Quaia for our task of finding large spot structures. We provide to the community these 3 catalogs that we hope will be useful for other colleagues. Our tests of radii, densities, and profiles are all consistent with the mocks where lambda CDM was assumed. And if you're interested in working with the data, it's not yet out. If you drop me an email at this email address, or you talk to me during a coffee break, I'll put you on my mailing list, and then you'll hear when they're out. Of course, we want to further extend this work with some synergies with upcoming surveys, Euclid, maybe even X-ray, Eurozeta. Look if the properties that we have observed are correlated with some other properties that we can extract, or radiations along the spectrum. And we also want to cross-correlate with work that got published, a work of ours just 2 weeks ago, regarding the radio loudness of these same quasars. Could it be that radio loud quasars particularly like to be in the center of clusters, or they actually like to be somewhere in between in the density profiles when you look at voids. And eventually we also want to move into testing some cosmological tensions. As I said, we are in the redshift regime that overlaps with the cosmic noon, which is an area that's of high interest and where an ISW sign change is expected by some newer models. This would be something that we're all excited about doing in the future. Thank you for your attention.
What
was the color code on the last slide?
Sorry. Sorry for the small font.
The blue ones.
The blue ones. Okay. Solid is profiles.
The colors. What is the difference between the three colors?
Right. Dark blue are voids that are within a larger underdense environment. So it's like a void within a void. And lighter is a void that's located actually in some kind of an overdensity.
That's what I asked. Okay.
you know?
Yeah, thanks to Shannon. Right now, I'm more in the third, I think, slide. You show a histogram and you were talking about cutting between, I think that was like, yeah, this one, 0.8 to 2.2. But if you're considering this based on some, I don't know, for example, 0.8 is probably Euclid, 2.2, I don't know which survey. But is there any other reason you're cutting these like redshifts?
I think one other reason was that there was a previous work in SDSS that was within this redshift regime. It would be this one, if I'm not mistaken, that was exactly this one. And another reason would be that just looking at the N of Z distribution, we have this dip that's a little bit suspicious and this bump over here. And at least
from up to 2.4 is still the same, isn't it?
Yes, we could have cut it somehow deeper. In my memory, maybe Andres remembers it differently. It becomes some kind of a science legend, but I remember it. I'm being conservative and cutting here, and then also 2.2 is just a rounder number than 2.25. That's my honest reply.
Maybe analyze the shape of the voids and the clusters. I mean, with some very simple factors of the axes and so on.
You mean the shape of the voids in terms of being
Actually, I'm wondering about the 250 megaparsec size voids, that they are round shaped or it's some kind of elongated two smaller voids joined together or something like that.
Thanks for asking this. I want to say that our work was also facilitated by other colleagues, and actually in the last coffee break, Agnes, who is now starting as a master's student, has looked into them, and this is something that we also indeed want to investigate further. And she has discovered some funny shapes. Maybe we can talk in the break together with Agnes. Sorry for putting you on the spot. And yes, but this would be indeed interesting.
One more, yeah.
Just a follow-up for the cutting of the quasar. Is this before or after void finding? Do you cut this? Because
Before.
it feels like it would be nice to maybe do the void finding on the full thing and then cut, and then you would have less edge close voids.
I see that you have technical experience here in the void finding. We extended our void finding up to 0.5 and 2.7. We get then voids within this range, and then we cut down due to some peculiarities of revolver. Maybe you were intending, maybe this was what you were aiming at.
I didn't have any intended, so I'm not sure what peculiarity you mean. By the way, if you want something changed in the revolver, probably I'm the person.
I heard stories about you from yes. I will bother you, but yes, to answer your question, we run the void finder on a wider redshift range, and then we restricted ourselves to avoid this kind of edge effect.
Okay.
Thank you very much again.